In this segment, we will talk about an example where we want to be able to see that if we know what the absolute relative approximate error is, can we figure out how many significant digits are at least correct in my answer. So here is the example which is given to us, which we are asked to solve. There are 6 terms of the Maclaurin series for e to the power x. We are calculating e to the power 0.7, and then we want to be able to figure out how many significant digits can we trust in the solution. Keep in mind that when you are finding your answer, you are not privy to the exact value of e to the power 0.7. So if you look at the Maclaurin series for e to the power x, it is given by this particular polynomial. And if we want to use the first 6 terms of the series, so let's suppose 6 terms of the series, we can approximately calculate e to the power 0.7 as follows by using the first 6 terms of the series. And you can see that we have 6 terms: 1, 2, 3, 4, 5, and 6. And the value which I get from here is 2.0136. Now, if I want to figure out how many terms, how many significant digits can I trust in my solution here, then I'll have to calculate the value of the previous approximation, which will be, hey, what is the value of e to the power 0.7 by using the first 5 terms of the series. So here we have the first 5 terms of the series: 1, 2, 3, 4, and 5. And this number here turns out to be 2.0122. Now what I can do is, this is my current approximation and this is my previous approximation. So I can take my current approximation and my previous approximation and calculate my absolute relative approximate error, which is the current approximation minus the previous approximation divided by the current approximation, and I'm going to calculate it as a percentage, and this turns out to be 0.069527%. And by looking at this absolute relative approximate error, I can basically say that 2 significant digits are at least correct in my answer. How do I come to that conclusion? Because we have this theorem that if the absolute relative approximate error is less than or equal to 0.5 times 10 to the power 2 minus m%, then at least m significant digits are correct in my answer. So I basically applied that, because when m is equal to 1, epsilon a has to be less than or equal to 5%. When m is equal to 2, epsilon a, absolute relative approximate, has to be less than or equal to 0.5%. And when m is equal to 3, absolute relative approximate has to be less than or equal to 0.05%. And now I can see that if I look at this number right here, it is less than 5%. It is less than 0.5%, but it's not less than 0.05%. Hence, the number of significant digits which will be correct in the answer is 2. So m is equal to 2 is my answer. Now, sometimes what happens is that when people try to apply this theorem, they might get a little bit concerned about that, hey, I have to calculate it for 1 significant digit, then 2, then 3, then 4, and then see where it falls. You can also say that, hey, we are trying to figure out, hey, when is epsilon a less than or equal to 0.5 10 to the power 2 minus m? What is the largest value of m for which this absolute relative approximate satisfies this particular inequality? So you get 0.069527, which is my absolute relative approximate. When is it less than or equal to 0.5 times 10 to the power 2 minus m? So if I do that, I get this. taking 0.5 to the left hand side. Now here, in order to be able to find m, one of the ways I can do it is I can take the log to the base 10 of both sides. That's the easiest thing to do. You can take natural log as well. It will give you the same answer. So here I will get minus 0.8567. This will be equal to 2 minus m. That means m is equal to 2 plus 0.8567. And that's 2.8567. So the number of significants which will be at least correct will be 2. So by doing this way also, you are able to find out how many significants can you trust in your solution of e to the power 0.7 being approximately to 2.0136. That means you can trust this 2, you can trust this 0, but it's quite possible that more than 2 significants is at least correct in this answer. But it's only telling you that, hey, it's quite possible that more than 2 significants at least are correct in your answer, but we are from the theorem only able to say how many are at least correct. In this case is 2, so this is 1 and this is 2. And that's the end of this segment.